Namaskar. Now I will be covering about tolerable step and tolerable touch voltage. The previous video I have basically explained about the basics of earthing grid, and now I will go into tolerable step and tolerable touch voltage. This is the equivalent circuit during a fault. Now this is the normal equivalent circuit of the source impedance and the load. Now this path represents the normal equivalent circuit. During normal operation, when there is no fault, the load current will be flowing in this path. But when there is a fault, what happens? Let's say there is a fault in some equipment because of an insulation rupture, and the fault current flows from the source and it will get into the outer metal of the equipment and it will get into the earth grid. The fault current will see the source impedance, the fault resistance and the earth grid resistance as the main impedance along its path. Now, let's say there is a person in the vicinity of this equipment. If that person touches this equipment, he should not get electrocuted. That is the objective of our design. Now, this is the person. The person's body resistance is represented by RB, and then the person's foot resistance is represented by RF. Now RF is the foot resistance from the person's foot up to the bottom of the grid. Now this equivalent circuit will be reduced to this circuit. Now before I go there, I have already explained about E-touch and about V-touch and V-step. V-touch is the step voltage. V-touch is the touch voltage and V-step is the step voltage. Basically, touch voltage is the voltage from the person's hand to the foot, and step voltage is the voltage between the two foot of the person. And it is this voltage which causes current to flow through the human body, and if the current is high, it can cause fatality or death of a person. Now in this circuit, let me not consider this path where the load current flows. I am only concerned about the fault current. So I will represent this circuit as given below. Source impedance is there, source voltage is there, the fault resistance, the grid resistance is there, and the person body resistance RB is there, and since there are 2 feet, so they are in parallel, I will take it as RF by 2. Now this circuit has to be further simplified to a Thevenin's equivalent circuit. Thevenin's equivalent comes in the circuit theory. And those who don't know much about circuit theory, I will just tell briefly about this. Any network can be represented as a single voltage source in series with a single impedance. That voltage is called Thevenin's voltage, and that impedance is called Thevenin impedance. The Thevenin voltage is nothing but the voltage at the place where we want to study. Here the Thevenin's voltage is the voltage across the human body, that is from the hand to the foot or from the foot to the foot. And Thevenin impedance is the impedance seen at that location in the reverse direction. Suppose I remove this source, I short this source, and I remove this person and I connect a multimeter here and measure the impedance. That should give me the Thevenin impedance. So I will not go much deep into this Thevenin's network. As I told earlier, it is, if you go through circuit theory, you will come to know more about it. So here When this circuit is represented with the equivalent circuit, this is the Thevenin's voltage, Thevenin impedance, and the body resistance RB, and the current flowing here is same, the current to the body IB. Now we have to determine the Thevenin's impedance. How do we determine the Thevenin's impedance? It's very simple. To determine the Thevenin's impedance, all you have to do is just remove this source, short this source. Zs is in parallel with this. Rf plus Rg is equivalent to Rg because fault resistance is very negligible. And when Rg is parallel with Zs, since Zs is very less, it is equivalent to Rg. So this entire thing gets reduced to Rg. So Rg plus Rf by 2. Rf may be of the order of 0.6 ohms or 1 ohms or much less, and Rf will be high, maybe even in the range of sometime kilo ohms. So compared to Rg, Rf by 2 is high, so we can neglect Rg. Finally, the Thevenin's equivalent impedance here becomes Rf by 2. So it is Rf by 2. Now we write down the equation for this circuit. V Thevenin, this is a simple Kirchhoff voltage law. V is equal to I into Z. That is V Thevenin is equal to IB into Z Thevenin plus RB. As I told earlier, Z Thevenin is equal to Rf by 2. So finally this equation becomes IB into RB plus Rf by 2. This foot resistance is found out by empirical analysis. It is equivalent to 6 rho. As I told, empirical formulas are derived by experiment. So IB is equal to RB into 1.5 rho. Rho is the resistivity of the soil, and IB is equal to RB. RB is the body resistance. I have told previously, body resistance is approximately around 1000 ohms. This also has been determined by experiments. IB is equal to 1000 plus 1.5 rho. IB, what is IB? IB is the tolerable body current, the current which can flow through the human body and still does not cause death. So IB will be equivalent to 0.116 by root T. That is, we can allow 116 milliamps of current for 1 second in a person of body weight 50 kg, and that person will not die. That is, ventricular fibrillation of the heart will not occur. So the equation V Thevenin is equal to 0.116 by root T into 1000 plus 1.5 rho. Now this V Thevenin is basically the touch voltage. So the voltage which a person can touch and still not die is equivalent to this 0.116 by root T into 1000 plus 1.5 rho. Now let's say that the fault exists for 1 second, and let me consider a soil where the resistivity is approximately 200 ohm meter. So this equation becomes 0.116 into 1000 plus 1.5 into 200. So that is around 143 volts. So the touch voltage is 143 volts. So if a person should not die when touching a metallic object in the substation which is subjected to fault, the voltage should not exceed 143 volts. Suppose the tripping time is reduced to 600 millisecond, then the voltage, the safe voltage is up to 185 volts. Suppose the tripping time reduces to further less, 100 millisecond, the safe voltage allowed is 430 volts. So what you can observe here is this voltage is very less. If I have to restrict my step voltage in a substation to 143 volts. Later on you will find that my earthing grid design has to be sized in such a way that it needs to have lot of conductors. It is very difficult to achieve this design. Hence what we do is we try to increase the resistivity, rho, and we try to increase the resistivity by adding some gravel in the substation. I will explain about that in the next topic. Now let me go to the tolerable step voltage. When a person is standing, there is a voltage between the 2 feet, and that voltage has to be below a value so that the current that flows through the person's leg back to the leg does not cause fatality. Just like this equivalent circuit, I represent again one more equivalent circuit for the step voltage. This is the source and this is the impedance and this is the fault resistance. The only difference between this circuit and this circuit is the earth grid has been represented here as a distributed parameter. So I have represented the earth grid in bit detail. So what happens here, this entire thing is, this ladder network is the earth grid, and the person is standing here, his 2 foot are here, and this is the foot resistance RF and this is the body resistance RP. So in a substation, when there is a fault, the fault current flows into the earth grid, and when the fault current flows into the earth grid, there is a potential rise in the earth grid that is called ground potential rise. I'll explain about it later. Now this ground potential rise is not uniform. At different places the potential is different. So what happens, a person's left foot may be at, let's say, 2000 volts, his right foot may be at 2500 volts. So there may be a difference of 500 volts between his 2 foot, and that will cause a small current to flow through his body. So the current that is flowing here. Now similar to this equation, let us write down the equation. Thevenin's voltage is equal to body current IB, this is the current IB that is flowing here, into RB, this is RB, plus 2RF, since there is 2 foot. So that becomes IB is equal to RB plus 6 rho. RF is equal to 3 rho. As I explained there, it is based on the empirical formula. So IB is equal to 1000 plus 6 rho, because body resistance is equal to 1000 ohms. So IB is 0.116 by root T, as I have explained earlier, into 1000 plus 6 rho. So for 1 second it is 0.116 into 1000 plus 6 into 200. I am considering the same example as previously, the resistivity of soil equivalent to 200 ohm meter. So the step voltage will be approximately 243 volts for 1 second. For 100, if the fault is cleared in 100 millisecond, the step voltage which can be allowed is 720 volts and below. So as I explained in the previous case, these voltages are very less. In order, if a person touches this about 243 volts, it leads to death, and I have to design a substation where the voltage is below 243 volts. Then I have to put lot of copper bars or lot of GI, lot of galvanized steel below the earth, and that becomes very costly. Hence what we do is we try to increase this part. So when we increase this part, this voltage increases. That is, that tolerable limit goes up. I will explain about it in the next section. So basically what I have covered now is, in the previous topic I explained about the basics of earthing, and in the present topic I have explained about the tolerable step and tolerable touch voltage. In the further topic, I will explain about the step and touch voltage that will actually occur in a substation during a fault. I will be explaining about it. Thank you.